Okay, welcome to the very first lecture in this course, which is ME 5228 Engineering Acoustics. I hope that you have already seen some of the stuff that I have posted on Moodle. We have basically the how this course is going to be run, the books and the curriculum that we are going to follow. It is going to be run in an asynchronous mode, which I had put there already in the documents. For those who are not familiar with this term, basically this means that I am going to run this as the videos will be recorded like the one that you are seeing right now, and this will be available for you to see at a convenient time for you, and you can also pause and view this. You don't have to see this in one go. To make your life easy, what I'm going to do is to not record more than maybe about 20 to 25 minutes usually, not more than that, so it's just like half a class. So the intent is to post 4 to 5 videos a week, and allow you to kind of ease into this, look at this, and the interaction classes are placed in such a way that, for example, if I upload 2 videos for maybe say 2 videos, which is about 50 minutes, which is equivalent to theoretically one class, but I may cover a little bit more simply because nobody is interrupting me asking questions, right? So therefore I will upload this on Monday, for example. Then I expect by Thursday, when we have an interaction session, that most of you would have seen this video and have questions, queries that we can discuss on Thursday. So depending on the amount of interaction, the intent is to have at least half an hour of interaction, and maybe a little bit more, up to 45 minutes. That is the intent during the G-slot class. So obviously we are limited to 50 minutes. I don't want you to hold you back if there is a live class that you have to attend. So again, some more videos will be uploaded on Thursday, and the hope is that you will be able to see those videos or over by the weekend, and then post again some questions so that we can have a lively Monday interaction class. So that's the goal behind this asynchronous mode. And of course, every now and then assignments will be given to kind of work your way through, understand the material. And of course, the intent is to hold 5 quizzes, possibly one in this month of February, and maybe 2 each in March and April, so that we will and of course this will depend on the module and the rate at which we are going, which is why in February I plan to have only one. So we need to reach a point where we can conduct a quiz. So possibly one in each module, 4 to 5 modules, so we may have one in each module. And as I indicated, this will be I'll take the best 3, and the assignments of course will be a combination of pencil paper and some little programming. Prefer to use MATLAB or Octave. Octave is an open source software. Alright, so let's delve a little bit into this. Initially we'll be doing the introduction and measurement part of it. The measurement is important because you will see that to identify a problem I need to do measurements. So we'll go through that. Let's look at start with a very basic effect here as to what is we'll start with what is acoustics, right? So of course most of you at some school level, for example, would have done something with sound waves. So acoustics is basically the science dealing with the generation and propagation of sound waves. And as engineers, we are not only interested in the generation and propagation of sound waves, but also the control of or reduction in the sound that is produced. So therefore we will try to call this as acoustics, and noise control, which is basically dealing with the reduction of the sound. So what is wave? Of course, waves, there are various types of waves, which are basically disturbances that propagate in a medium. You have both energy and momentum propagating. The particle that is disturbed is not transported, but it is simply disturbed locally, and it oscillates back and forth about that. So that's a typical characteristic of a wave. And if you have what is called as a traveling wave, so which means that in a kind of a very large domain, then the relative amplitudes keep varying of the particle oscillations keep varying, then it is called a traveling wave. This happens in very large spaces, and if the relative amplitudes are reach a constant ratio, then you have what are called as standing waves. So you have a traveling wave where I don't have a boundary, for example, and I will set up standing waves when I have a boundary, because when it reaches a boundary it is going to reflect, and then there is a pattern that these waves set up, which is why the relative amplitudes remain constant. So these are just concepts, various concepts that you should familiarize yourself with. As we go along, we will deal with various things related to this, right? So you have a traveling wave. So there are a lot of terms that I will throw at you, but you can look at this. One of the advantages of an asynchronous thing is you can pause. You can go look at what I mean by this. I've already explained, but if you need more things, you can always go back and look at things. So one classification is traveling wave and standing waves. The other classification is based on the kind of particle motion. This is first thing that we will look at is what is called as a longitudinal wave. Acoustic waves are basically longitudinal waves. The longitudinal wave, by definition, the particle displacement is parallel to the direction of propagation. So I will show you an animation here. So you can see that this is of course from Dan Russell in Penn State University. So you can see here that on the left I have a piston, which you can think of as a speaker or your mouth, which basically is moved, because of the speaker diaphragm vibration, I have the particles disturbed in the medium, and you can see that the wave is propagating. So I hope you are able to see that there is a wave propagation going from my left to right, and also when you see this video, your to right. All right. So you can see this is energy is propagating, but the particles themselves do not travel with the wave. It is only the energy and momentum associated with the wave that travels. So you need a disturbance which will generate these kind of waves. So that is what is the generation part of it, and you saw the propagation part of it. Once again, to emphasize, the red dot that you saw in the previous thing, we are now doing a few things to see that. The red dots that you saw in the previous thing, they only move locally. You can see that red arrow is kind of going back and forth, but the wave itself is going away, right? The wave starts from left and will go all the way to the right and out of this block, because we have got a limited viewing span. But the red dots basically stay locally. They just move back and forth at that local area. So this is a characteristic of the wave that you need to keep in mind. So the other type of wave is the transverse wave, where the particle displacement is perpendicular to the wave propagates, say, left to right, but the particle moves up and down. So that's called a transverse wave. So visualization again here, thanks to Dan Russell from Penn State. So you can see that the particles, the wave is propagating. I hope you are able to see that the wave is propagating from left to right, and the particle moves up and down. So that is a transverse wave. Very often people look at your experience from childhood as if I throw, for example, a stone into a pond, you will see waves propagating away, water waves propagating away, and we tend to think, and if you see that, you will see if there's something floating on the water, you will see that bobbing up and down, and people tend to think of water waves in water as water wave, but unfortunately it is not. It's a combination of longitudinal and transverse waves, and the particles do a circular motion. So here is a water wave. So you can see that on the surface, so if you notice, there is two particles, one which is on the surface and one a little bit below. One of the things is, of course, the disturbance is more on the surface. You can see that the particles which are towards the bottom of the pond do not move. The ones at the top move the most, and it slowly decays. So you can see that there is a combination of both transverse and longitudinal effects. So the particle tends to execute a circular motion. So to us, of course, as a casual observer, it seems like it is bobbing up and down, and it is a transverse but if somebody asks you, please tell them that no, waves in water are not purely transverse waves. There is a combination of transverse and longitudinal, and therefore you get what is called as a water wave, which is unique from that. Now there's another class of waves. So this is longitudinal waves, transverse waves, water waves. Then there are surface waves. For example, in earthquake scenarios, you have what is called as a Rayleigh wave. So this is, you don't need to, if you are interested, you can go explore what is a Rayleigh wave. But there are so many waves. There is a Stoneleigh wave, there is a Rayleigh wave, there is what do you call P wave, S wave, so many different categorizations that happen. See, in this case, a longitudinal wave, of course, the medium is also important. It can be in a solid, it can be in a liquid, it can be in a solid also, air also. So Rayleigh wave looks like this, again thanks to Dan Russell, but you see that it's a kind of a surface wave. With a kind of you see the thing that is pointed out is that the rotation direction, so it's almost like a circle, similar to water wave, but the rotation direction at the top is opposite to the rotation direction at the bottom. I hope you are able to visualize that as you see that. So this is going in a anti-clockwise direction, whereas this is the one below the subsurface is going in a clockwise direction. So these, as I said, I should thank Dan Russell from Penn State University for using these so that it's a nice visualization, so I don't have to reinvent the wheel, and I can simply use this and show you what is going on. Alright, okay, so you have traveling waves, you have standing waves, you have a longitudinal wave, transverse wave, water waves, Rayleigh waves, Stoneleigh waves, so many different classifications based on the type of characteristics associated with the wave. The other kind of phenomena that we'll quickly look at is what we call as these things you are aware of, but just to kind of summarize it here before we go into our subject, which is acoustics in air. We have reflection, which everybody is kind of aware of. If you go as a kid, probably if you have gone to a hill station, one of the things you will do is to shout, and then you can see an echo come back, which is basically reflection. So effectively this is a change in direction, and usually it's between two media, or so in air it goes, and then there's a wall, which is another medium, and then it reflects from there back into the air, medium of origin, right? So that's reflection. Then you have refraction. Many of you would have studied a prism with white light going through that, and then it bends and so on and so forth. The same thing happens with sound. Acoustics also, you have that. Of course, light waves show refraction, but basically it's bending of waves as it goes from one medium to another, say from air to glass or air to water. And this is because of different speeds of propagation. So same philosophy that you had in optics. The speed of light in air to speed of light in say a glass prism are different, and that is why you have refraction. So there is a bending in the direction of propagation. So this is refraction. Of course, just visualized over here. You can see that light comes like this, the wave comes like this, and then bends. So the original angle is theta 1, and then it bends to an angle theta 2. So this theta 1 to theta 2 change depends on the speed of wave propagation in the medium. Then you have interference. Again, this is true in optics as well as in acoustics. When two waves meet each other, you can have constructive and destructive effects. So where amplitudes add and where amplitudes subtract. So this is called interference. Again, visualized through this, you can see I have two sources. Imagine I have sound generated from two speakers, and the sound waves are propagating. The two waves meet, and when they meet, have zones of silence. So if you are here and let's say these are in phase, so the beauty of that is you will hear nothing along this line, similarly nothing along this line. But if you are sitting here, you will see a big amplification in the overall sound that is produced. So this is interference. And you also have diffraction, which is bending of waves around an obstacle, opening or obstacle. So this is the diffraction effect is more significant for larger wavelengths in most cases. So here is a visualization. You can see the wave which is generated from the speaker. It propagates and then it kind of bends over this obstacle. You can see here at that edge it basically bends over and then propagates in this direction. So that is diffraction. All of these effects are important. We will see at least the reflection part of it. May not be much on interference or diffraction, but reflection and refraction is something that we will see as we go along the course. So that's some phenomena associated with the waves. Now we get down to so this whatever I have described up to this point of time is basically valid irrespective of whether it's a sound wave. Of course, for a light wave, you have been told electromagnetic waves don't require a medium to travel, whereas a sound wave does require a medium. So far, we have generally talked about waves, properties of waves. So therefore, the fact that it is a transverse wave or it is a longitudinal wave or a standing wave, a traveling wave, reflection, refraction, all of these happen for all kinds of waves. But now our focus is going to shift to sound, which is what is of interest in this course. So the question that we have is what is sound, right? So we saw acoustics is the study of propagation and generation of sound waves. We are interested in acoustics, although we quickly looked at various kind of waves. Sound is essentially a sensation that is produced in the human ear. So this is something that we hear. Of course, all living things, I don't know about plants, but at least the animal kingdom, they can sense sound. I think the snakes are the only things which probably react more to vibration rather than sound. Sound is essentially a sensation that is produced in the human ear, and that is because we talked about waves. These waves go into the sound and they create the disturbance in the atmosphere, which is called pressure fluctuations, which is about the mean atmospheric pressure of 100 kilopascals, which is 1 bar typically at mean sea level, right? The amplitudes of these sound waves actually are very small. They typically range from 20 micropascals, which is called as threshold of human hearing. If the amplitude is smaller than that, then we don't hear it as a human being, normal human being. And typical range is from 20 micropascals to 10 pascals or maybe even more. So just to visualize how this, how do we perceive sound, here is a animation of a eardrum. So you can see that the sound wave that is coming into the ear through your ear, it goes in and then it excites. This is the middle ear and then of course the inner ear where the processing happens. So you can see that it goes and excites this middle ear. They keep moving back and forth as a response to this, and then the cilial hair and the inner ear nerves basically pass on this information to the brain, and then you are able to perceive this, just like what you are doing right now. Apart from the amplitude range, human beings can hear sounds only limited to 20 hertz to 20 kilohertz. So this is something, our ear structure is such that if it is below 20 hertz, we will not be able to process that sound. And above 20 kilohertz, again, we will not be able to process sounds. So some animals, for example, elephants are very good hearing below 20 hertz, which is they can even hear what is called as infrasound, because it is below 20 hertz what human beings can hear, right? And you have dogs which can hear well above this. A dog whistle, for example, cannot be heard by a human being, but a dog will respond because it is tuned to something which is above 20 kilohertz. So you have a frequency range for the sound that we can hear, and also a range of amplitudes, at least a minimal amplitude above which we can start to hear, right? So these are some things that you keep in your mind, that these things that characteristic of the sound, right? All right. Now, as I said, we saw earlier wave types. Sound waves are longitudinal waves, where the air particles move back and forth parallel to wave propagation direction. So in air, the sound wave propagation is basically classified as a longitudinal wave, because when I speak, the air particles are excited in the same direction as the wave propagation direction. So they can also be what we call plane waves. This is of course based on the propagation characteristics. So all sound waves are longitudinal waves, but within that longitudinal wave I can have what are called as plane waves. So if I confine this sound to travel through a duct, for example, you have an AC duct, and in most buildings, commercial buildings, you will see AC ducts which run. There is sound that is traveling through that because of the airflow through the duct. It generates noise. So it travels through that, and because it is in a confined space, it becomes what is called as a plane wave. What do we mean by a plane wave? In this case, the physical variables, we will see what those physical variables are. You don't have to worry about this. It's only a function of the length, and cross section really doesn't come into play, at least until a certain frequency. So you have plane waves. Then you have what are called as spherical waves. So this typically happens when sound is generated by an object and it radiates in large spaces. So if you are in a cricket field and you hear the batsman hit the ball, the sound talk comes, and then it propagates basically as spherical wave front. So the sound in increasing size of spheres, the sound energy is basically being propagated. This will also be true for machines, right? So the other thing which we won't encounter much is what is called as a cylindrical wave, where the wave propagation is in terms of increasing cylinders. This happens in a hose pipe, for example, but we will not do much. So typically plane waves and spherical waves. Spherical waves happens in large spaces. This is the actual, in reality, waves are spherical waves, and actually plane wave is a kind of a special case where if you confine things to travel, the sound to travel in a confined space, then you could treat it as a plane wave. So these are the two types of sound waves that we have. And then what is noise? I think we will try to wrap up this session with a brief introduction to what is the difference between when we call sound as opposed to what is basically noise, right? So noise is basically sound that is annoying. So if it is not annoying, it will be music, I guess. So one man's music, of course, can be another man's noise. For example, if it is rock music, I may consider that, being an old man, that to be a noise, whereas to someone it is music. So there is a certain subjectivity associated with this classification. Missionary sound, by and large, people will agree, is noise, which is unwanted sound, unless of course you are the one owning the machine and making money out of it. The question is, why should we bother about noise? After all, these machines are generating sound, which is of course annoying, but so what? The fact is that this can become a serious health hazard. If you are exposed to really loud sounds in a factory, for example, I don't know if you people have gone to a factory and heard hydraulic presses in action. These are used basically to stamp parts, right? So for example, if you are looking at making of a cycle chain, the sprocket basically has, if you look at it, the sprocket basically has pins connected to plates. These plates are basically made by press, in a hydraulic press, by stamping it out. So you have a huge force coming and punching this hole in a very thick steel plate. So it creates a lot of sound. And if you are a worker exposed to this sound over a period of time, you will lose hearing. So something very serious. So we need to do something to get that sound down. Fortunately, there are government regulations which protect the workers as well as consumers. There are demands from industry to make products which satisfy this kind of noise level, which is healthy. And today, fortunately, not only from a point of view of health, but one of the desirable product attributes that is demanded today is low noise, which we call refinement. So you want to buy a washing machine that makes the least amount of noise. You want to buy a vacuum cleaner that is, between 3 vacuum cleaners, if one of them is relatively less noisy, or a mixie, I would rather buy that because it's a desirable product attribute. So that is something that is very important. So I think we will let's see what we have as the next slide. Let me just see if okay. In this the basic course is driven, even though it's called engineering acoustics, we are as an engineer we are looking at noise estimation. We are interested in reducing the sound generated by machines. So as a mechanical engineer, typically we are trying to, as I said, either from a health perspective, it is making too much noise, we want to bring it down to levels which is more healthy, or as a product attribute where it is not an issue in terms of health, but I use it as a product differentiator. So in either case, I am interested in reducing the sound. To fix it, of course, we know amplitudes and frequencies. In the next lecture, I will show you how do I extract these amplitudes and frequencies, how do we quantify these. So what I will do is I will use an audio file that I have generated by my whistling, and we will run through. Of course, later I will give you an assignment to try it out on your own. So we will characterize the amplitudes and what are the frequencies, we quantify that, and this is done by measuring sound pressure. So how did I get the measurement done? I had a microphone, I whistled into the microphone and it stored that thing in an audio file, right? So we will see this noise estimation. To do noise estimation, we have to do a measurement, right? Otherwise, how do you know what is the level of the noise? So therefore, that is why right at the beginning of the course, we are trying to quantify the noise, as well as look at the quality of the characteristics of that noise. So we will come back, we will look at how to quantify this and how do we do this by measuring sound pressure and what are the things that we need to do. So I will stop here. This is the first lecture and we will continue from here. As I said, I will start the next lecture. What I will do is when we say amplitude and frequency, as I said, I will use a bit that I have recorded from my whistle, and then we will basically do a processing. As I said, we will also do an assignment a little bit later. So you can see that there are a lot of frequencies that are required, that are present, and of course some which are very, very dominant in terms of the levels, right? Okay, I will stop at this point of time. We will continue with the next lecture starting from my whistling.